All right, welcome to our physics marathon. Now we're about to start now, and let's just hope that this marathon uh, will become useful to you, and all the materials that will be provided here and the working out of the question. I hope that it will be um, useful, right, in your success in your CXC exams. All right, so let's begin. Well, let's start by just looking at what is happening on the screen. Here we're seeing a obviously a set of persons running, right? So this is basically you guys, running towards the finishing line, right, or the finish line. The race is going to be hot, right? But only the fittest of the fittest will survive. And so let's see if we can proceed. Perfect. Now, I deliberately um, chose these questions, and the reason for doing that is because of the selected topics that were issued out by CXC. And one of such topic is the gas laws. All right. When we talk about gas laws, you'll hear us talking about Boyle's law, Charles' law, and pressure law, right? Now here we have a question. It says, in an experiment to investigate Charles' law, a physics student used a fixed mass of dry air trapped in a glass capillary tube as seen in figure 1. It says here that the student recorded in table 1 how the length of the air column varied with temperature. All right, so here we're seeing the table right here. This is the table. This is obviously the setup of the experiment. So I'm assuming now that the student would have altered the temperature, right? And with that, the the height of the air column would have changed, right? Now we have this table. The first thing they ask us to do is to complete table 1 by calculating the temperature T in kelvins. So by looking at the data that was collected, it is clearly showing us that the temperature was calculated in degrees Celsius, right? Now the question is, how would we possibly convert this from degrees to Kelvin? Because there's a set way how we can do that. So that's a question I'm going to just give you a few minutes, right, to think about it, and then I just want to hear what you guys have to say about that. All right. So think about it to see how would you convert from Kelvin to degrees Celsius. Well, from degrees Celsius to Kelvin rather. Now, for this case, right, this is what we'd have to do. So first, we have to remember that whenever we want to convert from degrees Celsius to Kelvin, we would use this formula that says T, which is the temperature in Kelvin, is equal to the temperature in degrees plus 273. All right. And this is, yeah. So this, in a sense, now will uh, tell us the temperature in Kelvin, right? So this is basically a small formula that we can use. Now, there's something important that you can also do with this equation. What if you had the temperature in Kelvin already and you want to find the temperature in degrees? Then all you would do is to just simply transpose to make theta becomes the subject. So theta, right, would be equal to the temperature in Kelvin minus 273, right? And at the end of the day, your answer is going to be in degrees Celsius. Okay? That is if you wanted to find the thing in terms of degrees. But now, seeing that we just want to find the temperature in Kelvin, then we would use this format. So, simply put, I would go ahead and say T is equal to, now the first thing that I need to convert here is 14 degrees to Kelvin. So I'll put 14 right here, and I'm gonna add that to 273. When we work with that mathematics, right? 14 plus 273, right? T becomes 280 87 kelvins. So right now in this part of the table, you just go ahead and write 287. You don't need to write kelvins again because Kelvin is already here as the unit. So I'm going to just go and write out the others. So this would be 301. This is going to be 313. The other one is going to be 330.5. Then the other is going to be 351. The other one is going to be 358. All right, so I'm going to check that last one and verify as well. Yes, yes, indeed. All right, perfect. So now that we have that information, you would have scored 3 marks as it relates to um, that question. Now, let's continue. They are now asking us to they are now asking us to use the readings from the completed table to plot a graph um, of length of the air column, right, which is in millimeters, against temperature, which is obviously in kelvins, on a graph paper provided. Now, they also gave us some additional information. They told us that the the L axis, which is basically your Y axis, should start at 140 millimeters, and the T axis, which is the temperature axis, should start at uh, 2 270 kelvins, right? So let's go ahead and see if we can do that quickly on a graph paper. As a matter of fact, just pause the video, right, and try it for yourself. Uh, bear in mind, all of these conditions that they would have pointed out to you. All right. So do that for me quickly. All right. So perfect. So there's a small formula that we generally use for this case that says T is equal to theta plus 273. We don't have to use the point 0.15 because in some regards, in some textbooks and so forth, they don't really pay attention to that 1.5. I mean that point 0.5, I should say. That 0.15. But it's necessary when you move on to the cape level. So you could just simply use this number, right? And obviously, theta here just speaks to the temperature in degrees. So all you would just need to do now is to just say T is equal to 14 plus 273, and you're going to get your value in Kelvin, right? So all we're going to do now is to just populate the table. So this becomes 287. The next one will become 301, right? 313, 330.5, and the next value here is going to be 351. The other value is going to become 358. Following so far?
Yes, sir.
All right, somebody got dropped off. I think the other student got dropped off. No, you have your graph papers, right? Because we would have said that you're supposed to have at least some graph papers.
No, sir, I don't have any. I'm sorry.
Oh my goodness. So you didn't get that email, by the way?
The one about, oh, I saw the one about the marathon, yes.
The one about the marathon, you got it?
Yes, sir, but I didn't see the that you need graph paper.
Oh, okay, okay. And you have none whatsoever?
No, sir.
Okay, yeah, because we want to practice graphs, right? Because that is a must in these in your exam, of course. Now, so the question is to use the readings from the completed table. We want to plot a graph of length of the air column, which is in millimeters, against the temperature, which is in Kelvin, on the graph provided. Now, they would have made mention of something here. It says that the L-axis, which is basically the length axis or the Y-axis, they said that it should start at 140 millimeters, and the temperature axis should start at 270 Kelvin. Okay? Do you know how that would look on the graph if you were to start at those axes?
Like it would look a bit higher.
All right, I know there's a whiteboard thing, and do you know how to use that whiteboard thing? That.
Yes, sir.
All right, go ahead and set up your whiteboard thing on your. I don't know if you're using a computer, but you probably should. Right, set it up and then now show me what it possibly would look like. Because I mean, I want to be sure that you understand that. You get me?
Sir, it's not allowing me to.
Or you talking about on my computer? That's what you mean?
It's not allowing me to do the thing. It says it's disabled.
Okay, okay. All right, I guess it might not work then. All right, either way, let me show you what we would do in this case. All right. All right. So typically, this is our graph paper, right? They say we should start um, at one, what was it, 140? Yes, it was
Yes, sir.
140, right? So all you would do is to just start here. So 140 on this axis. Then now for the other axis, do you remember the amount that they said you should start by?
Was it like 270 or something? I don't remember.
Yeah, let me just check quickly. 270. All right, good. 270. So typically 270 will be right here. It's kind of a little bit tricky, but what they would have done, they did something what we call breaking the graph. Now, it is something that is applicable in physics, right? Where you can start your axes at a different value from zero, right? Just to allow the graph to look neat, of course, and so that you have a good representation of the data. Now, my question is, what scale do you want us to use in this case for your y-axis?
Can I see the values?
You want to see the values? All right, give me a second. There you go. Remember, I sent you the PowerPoint now, in the chat. So I want you to download it.
You can just go by 20 or um yeah 20 or 50 even. It's like
All right, so give me the scale basically for the y-axis. What scale would you have here for the y-axis? Tell me.
so like 140 then 190 and then um 240
Hold on, hold on,
290.
hold on. Give me the scale. 'Cause remember now, every graph has a scale, right? You remember what we mean by the scale of the graph?
So 5 to 1 centimeter, 50 to 1 centimeter,
So you're saying 5 to 1 centimeter,
50.
or you're going up by 50?
Yeah, because I have to
Why?
add 50 each. So,
But why you want to go by 50 though?
but isn't it 140?
What do you mean? What is 140? Yes, we started off with 140.
So if you go by 5, wouldn't it just be like 145
Okay, that's what
next?
you mean. Okay, I get you now. So you're saying that for every centimeter, that is equal to 5.
50.
No,
Yeah.
man. Why you say 50? I'm still trying to understand why you're saying 50.
Because wouldn't the next one be 145 and wouldn't that be too small?
Repeat that for me.
Wouldn't the next one be 145 and then that would be too small?
I can't say it would be too small. Not necessarily. It doesn't have to be too small. So if we say 145,
As
then
in,
next.
no, as in like, because the most you're going to get out of that graph would be like up to maybe 350 or something. I don't know.
Remember the
And it
highest.
goes up to like,
All right. So remember the highest value in the table is for the y values is 182. All right. So if you go by 5,
my bad, my bad.
yeah, yeah. So we're talking
Okay,
about the y-axis. You get me now?
yes, sir.
So what is the concrete value that you're going to tell me to go up on here? Are we going to buy
Five.
five? So normally when you're writing the scale, you should say, x-axis, or y-axis rather, is equal to 1 centimeter to 5 millimeters, or you could say 5 units. All right. So the next value here that we're gonna have is um, 145. But you see, I think it's best if we say 2 centimeters equals 10, just make it look a little bit more neater. You follow me?
Okay.
Yeah. All right. There's something here. Okay. Let me check something here. This thing is right. Okay. So scale, right? Y axis 2 centimeter, right? Gonna equal to 10 units. Let's hope that we get a good representation. So this is gonna be 150. Next one is gonna be 160. Right. Next one is gonna be 170. Next one is gonna be 180. It's somewhat a little bit small, if you see what I mean. It's kind of a little bit too small. You get me?
Yes, sir. Can go by two maybe.
So how much is what you want to go up by now?
Probably like two for every five. I mean every one, sorry.
All right. Say it again.
Two for every 1 centimeter.
Two for every 1 centimeter. So we could say 2 centimeters for four. Is that what you're saying?
Okay.
All right. So that's going to be 144, 148, 152. Right. Then the next number is going to be 156, 160. Right. 164, 168, 172, 180. Well, not well, 176 rather. All right. What about the next axis now?
By five as well.
All right, by five. You say. All right. Let's see. So this is going to be 275. So we're doing every 2 centimeter. Next one is going to be two. think we probably should do 10. What do you think? 10, would 10 make?
Yeah, 10.
Yeah, 10. I think 10 would make it a little bit better. It's a little bit tricky too because the graph here is a little bit small. So that's 320 right here. It's gonna be 330. Uh, will it make it? It's not gonna work.
Then probably two, sorry. The last one.
No, we need a bigger number, right? We need a bigger number.
15.
Yeah, let's. All right, so if we're doing 15, the next number here would be 285, right?
Yes, sir.
The next number would be 290. Would that be correct or no? Or 300? Which one?
300.
300. Then we have 315. Then we have 330. Right. Then we have 345. Then we have 350. Not 350. My bad. That would be 360. 360. I think that would cover it.
Yes, sir.
All right. So all we just need to do is to kind of label up our graph now. So let's put in for the x-axis. We said 2 centimeter is equal to 5 units. Not 5, 15 rather, 15 units. And then now we need to just label this to say t. Sorry about that. T is equal, well, we're just labeling up the axis. So t in bracket we put Kelvin. On this side we can put L, and in bracket we put millimeters. The task now is to plot the graph, which um, shouldn't be that hard, right? Now, there's a little bit of a trick right here. I mean, the scale that we use, the values in between are going to be a little bit difficult to find, but we have a way that we can find those small boxes. I don't know if you understand what I mean, but these smaller boxes right here, right? How do you propose that we find the values of the smaller boxes? Do you know how to find those smaller boxes? Because we need to plot the data now. The first point that we need to plot are basically 152 and 287, right? Clearly, it's not easy for me to find 287. So how do you suggest that I will find 287?
So each small thing is 1.5.
All right, so you're saying that each of them is 1.5. Which for which axis? Which axis are you referring to?
X.
x-axis. How did you work that out?
Divide it by 10.
What you divide by 10?
15.
All right, yes. So because the scale, right, is going up by 15 and there are 10 small boxes in between, then you just divide by 10. Correct. So for each of these small boxes, they value 1.5. So let's see if we can find where uh, 287 would be. But I guess 287 would be right close to the in between the this first box right here, right? It wouldn't be the first box. It would obviously in between. So we can just narrow that in between. That's how you go.
Yes, sir.
All right. So let's see if we can plot the first point. So the first point is going to be somewhere here. All right. Now for the second point, we're plotting 301 to 153. All right. So we need to find obviously 301. So let's see if we can find that. Oh, this is 300. Oh, I forgot in I thought this was 310, but this is 300. It kind of wrote a little bit funny. So the value we're looking for is at 301. Okay. So 301 then would be practically um, almost on the line. And then now we're looking for 158. So how could we find 158 over this side? We're going up by how much here? We're going up by 4. So 4 divided by 10, right? So each of these small boxes represent zero point 0.4, and I know you would agree with that, right? So we're looking for, so would it be in the middle right here? 158 should be in the middle right here.
Yes, sir.
All right, perfect. So let's locate that point now. All right. What's the other point that we're looking for? You remember the other point?
No, sir.
Okay. It's 113, not 113, 313 rather. Plot against 163. So on the graph right here, we're seeing 115. So chances are 113 is going to be somewhere right here. Well, let's just check. This is going to be 8. So 8 times 1.5 plus 300. All right. So it's closer to this one, to the ninth box. It's going to be closer to the ninth box. So we can go ahead and locate the ninth box here, and then now find 163. I would say it's going to be somewhere here, right? Because I mean,
Yes.
one 162 would have been in the middle, so halfway in between 162 and 163 is going to be 160. Yeah, halfway in between 162 and 164 is going to be 163. Yeah, so that's basically that one. And then now let's just see if we can do this quickly. The other one is now 330.5, so we can just narrow it at 330. We're looking for 170. So I believe 170 would be right here. Okay. Then now we're looking for 351. I believe 351 is going to be somewhere in the middle right here. Let me just check. All right. 179. So I'm going to work with this point. As you can imagine, plotting this on the computer might not be so easy. We want to plot the last point now. The last point here is going to be 358 versus 182. All right, I'm taking that's where the point is located. Now, obviously, we need to draw a line of base width. Would you agree on that part?
Yes, sir.
All right, cool. All right, that's my line of base width. That's the best I can get my graph right now because it's being done on the computer. Now, the question it continues. By the way, did you download the thing I told you to download?
The PDF?
Yeah, the PowerPoint. Yeah.
Yes, sir.
All right. So, what would be the next question related to this thing here?
It's loading, sir.
Okay, okay. All right. So the question would be, right? The next question would be for us to uh, calculate the slope of the graph, right? You know what the slope of the graph is, right?
Yes, sir.
Okay, good. So what point do you think I should choose on the graph here for my slope?
One that isn't being used.
One that isn't being used, exactly. Well, actually, two that isn't being used, right? Or in other words, um, we should choose 2 points that are not from the table, but they must be from the line of best fit. Correct?
Sir.
All right. So we want to choose a point that we can easily read the values. Do you see any point here that might be easily read that we could possibly use?
Read.
Say it again.
Um, 745 and 176.
You say 176,
Yes, and 745.
745. I mean, you said 745? I didn't get that.
Oh, no. Oh, 345, sorry.
Okay, that's possibly the first one you're telling me. All
Yes,
right.
sir.
Let me just check and see. All right. So the thing is, it might not be completely accurate. You understand? When it comes down to this part, because of or the nature of the graph and all of that. So yeah, we're gonna just use this point as you would have stated, right? But yeah, what other point do you want to choose?
1, no, 315 and 164.
All right. So we have our y our x2, y2. Soon talk about that. Our x1 and we have our y1. Um, so let us use this for the x1 and the y1 point. That's going to be 315, you say, and 164 for the y for the x2 now. That's going to be 176, comma, um 345. Just estimating it. Now we need to find the slope, right? And we know that slope is the same thing as what we call the gradient. The symbol for gradient can either be S or M. Alright, so there are two symbols that we could use. If you're dealing with slope, typically speaking, they would use S as a symbol. If you're dealing with gradient, they would use M. So if you see any of those, then it shouldn't be anything of a concern. Now, you remember the formula to find the gradient?
Yes, sir.
Tell me now.
Is it y2 minus y1 over x2 minus x1?
Indeed. So y2 minus y1 divided by x2 minus x1. Yeah, you're supposed to have a calculator though, right?
So,
Yeah, man. So help me calculate that now. I think I made a little bit of an error in terms of writing down the values for the first one, right? Rather than writing 176, this is going to be 345, and then now this is going to be 176, right? All right. So I guess if we just do the mathematics here now, we should get the value. So M or S is going to be equal to, so if we subtract these now, so 176 minus 164, numerator becomes 12. Divide that now by the difference of 140, possibly going equal to 30, right? So we have 12 divided by 30. Answer for the gradient is going to equal to 0.4. And I think we can just write a unit for argument's sake. What do you think the unit is going to be for this?
um, I'm not sure.
Remember now, how do we come up by the units? How do we get the units for anything, in this case? If we're dividing something by something, how do we get the units? Think back
T
about
over L or something.
it again.
T over L.
No, remember what we're dividing. You have to remember that exactly. So if you're saying T upon L, what will be the units?
TL minus 1.
Now, remember now, for the gradient, you're dividing the y variable by the x variable, right? The y variable is length. What is the unit for length?
Oh, mm over K.
Say it again.
Over K.
Yeah, millimeters over k, right? We don't want to leave the number hanging, right? We don't want to, but possibly it might not have a unit, but because we're dividing, you know, variables upon another variable, we could simply write a unit. You know what I mean? All right. Having said that, we would have just calculated the gradient, right? And that gradient is going to equal to 0.4. All right. So having said that, let's go back over here now. So we just did that. So our gradient is equal to 0.4 millimeter per Kelvin. Now the question is, what information does the slope or the gradient of the graph provide? Would you be able to think about that?
What does that mean, sir?
You asking me what the question means?
As in, like, what would be the answer for that?
Or you don't know the answer?
No, sir.
Okay, okay. But think about it though. Like we just did something a while ago, right? Firstly, let's look back at the graph shortly and just observe what kind of a graph are we seeing here? I mean, think about it. Examine the graph and see what you can get from this graph somewhat. Is there anything that you can make mention of about the graph?
It's steep,
Steep, okay.
steep upward slope.
All right. Think about the variables now. Think about the variables.
They are proportional, directly proportional.
All right. Very good point. So they are directly proportional. Now, whenever you have a directly proportional relationship, what comes to mind afterwards? Because I mean, once there's something directly proportional, there's another thing that comes into play. Not sure if you know, but think about it.
Pardon me, sir?
You didn't hear me?
No.
Yeah. So, uh, you said directly proportional, and that is very good. Now, whenever you have a directly proportional relationship, there is something else that we normally make mention of. Not sure if you would remember or if you can think about it. Right? Think about it and let me know. What else, whenever we talk about directly proportional, what else comes into mind at that point?
No, I don't know. Inverse proportional?
No, man, you have said the correct thing, right? But it's just no. So, what and what is directly proportional? Tell me what and what is directly proportional.
Millimeter and Kelvin?
No, we don't say it like that. We have to use the variables instead, not the units. So what is the unit? What is the variable rather?
X and Y?
Not like that.
Length and temperature?
Length and temperature. Yes. So this is generally what we're seeing here, right? You know what this symbol means, right? In the middle.
Yes, sir.
What does it mean?
Proportional.
Proportional. Now, whenever there is a proportional relationship, there is always what we call a constant of proportionality. Is that familiar with you?
No, sir.
All right, no problem. So in this regard, we can make this become an equation by saying, by just replacing the proportional sign and say L is equal to a constant, which is what we call a proportional constant, times temperature. At all times, you will have this scenario whenever you have a proportional relationship. All right? There's a constant of proportionality. This constant is not going to change regardless of the point that you use. As long as the conditions are maintained, right, in the experiment, then At any point you go up by, there will be a constant uh, a proportion, meaning that for every for every centimeter you go up, you go up by X amount of temperature. That's what we mean by constant proportional in a sense, right? So that is basically what we are seeing here. Now, mind you, we on the graph we're plotting length versus um, versus time, not time, versus T rather, temperature. So if I were to transpose this equation so that I have L divided by T, L divided by T is equal to the constant. Just a while ago, our gradient, we were dividing length by temperature. So for that reason, the gradient information is going to provide to us the constant of proportionality. Proportionality. And the constant of proportionality, as I would have pointed out to you, it's a fixed value, right? It just tells us that for every length that you move, right, I'm going to increase the same temperature, or for every temperature change that I have, it's the same amount of length that is going to be changed. So as I said, constant of proportionality. You get me? You want clarity, or are you good?
I think I get it.
You didn't get it?
I did.
Oh, you did. Okay, 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 great. Now, do you think you can tell me what Charles' law states?
No, sir, I don't remember that.
All right. So the question here is related to Charles' experiment or Charles' law. By looking at the data, right? Would you be able to can give me a little bit of information related to it, related to what you think Charles' law might be about? Because the experiment is related to Charles' law. The chances are you can look at the data or even look at the graph and give me an idea as to what is happening. And I best believe that you know enough, but it's just a matter of you just looking at the data and then giving me some information. You'll see. Let me show you the graph again. So this is analyzing the information. So by just looking at the graph, you would have said something very important already, right? Which is critical to Charles' law. You following me?
Yes, sir.
Perfect. So let's just put one and two together. So based on this, right? In Charles' law, obviously we're dealing with um, it's a little bit tricky from this experiment doing. I should point out that it's a little bit tricky because we can't completely use this to talk about Charles' law, right? Because Charles' law is really related to volume and temperature, but in this case they are using length and not volume. So that's kind of like the trick. But let's not pressure the issue too much. But by way of looking on the graph, right, what this is showing us, I don't remember Josh, right? It is showing us that as temperature increases, the length of the air column is going to increase. So in essence, Charles' law is now going to tell us that if let's think about it, if the length of the air column is increasing, don't you think that the volume is also increasing?
Yes, sir.
Exactly. So what this is telling us now is um, that there's going to be a directly proportional relationship between the volume and the temperature. So as temperature increases, I would expect that my volume of the air column is going to the volume of the air is going to increase. Hence why we are seeing that the length of the air column would have increased. Um, well, let's just state what Charles law states, and you can even write this down for your own benefit, right? Okay, so Charles law states Charles law states that the volume of a fixed mass of gas, the volume of a fixed mass of gas is directly proportional mass of gas is directly proportional to its absolute temperature provided that the pressure of the gas is kept constant. And for this now, the formula would be V is equal to the constant of proportionality times the temperature. And that should give you your 4 marks mainly.
Okay, sir.
Say it again.
Okay.
All right, good, good. Um, you're in a group with your students, right? With the other students,
Yes, sir.
and none of them have responded to the message that was sent.
Let me try to call everybody.
Yeah, because I mean,